In the previous lecture, we finished this example and you get Bayes' theorem. For Bayes' theorem, you say, suppose that a sample space, S is our sample space, is a union of mutually disjoint events. Here we have some mutual disjoint events. The union of them is our sample space. And suppose A is an event in S. It's an event from S. S is the sample space. Here we take only an event from the sample space. We denote it by A. And suppose A and all the BKs have non-zero probabilities, where K is an integer, where K between 1 and n. Then here we say the probability of BK given A, BK given A equals probability of A given BK, A given BK times probability of BK dividing by, this is summation. This one is summation. The sum from 1 to n. Here we have n b's. Okay, we say the sum of all n, so the sum of all bi's, the sum of p, which is the probability of A given bi times the probability of bi. Here, I'm going to take an example. If you have, let's say, b1, b2, b3, and also A, we say the probability of, let's say, b2 given A equals, it equals to probability of A given b2 times probability of b2 dividing by, here this summation is the sum of all bi's. Yes, I'm just going to write down. I'm going to expand the summation here. It is probability of A given A1, so B1 times B1, probability of B1, plus probability of A given B2 times probability of B2 times, so plus probability of A given A B3 times probability of B3. Here, if you have 3 B's, okay, then it could be like this. This summation denotes this, and this is the expansion of that summation. Here we take an example. It says, at the telemarketing firm, Fu, Raqib, and Lee make calls. The table shows percentage of call each column makes and the percentage of persons who are annoyed and hung up on each column. Here we have given this table. It's the percentage of calls done by Fu, and this is by Raqib, and also this is by Lee. And here also this is the percentage of hung up by Fu. This is the percentage of hung up by Raqib, and this is the percentage of hung up by Lee. Okay. Now, what should we find? It says find probability of A. Here we say we let A denote the event of Fu made the call, and B denote Raqib made the call, C denote Lee made the call, and H denote the event the caller hung up. And this is the caller hung up. Okay, it says find probability A, probability B, probability C, and also probability of H given A, probability of H given B, probability of H given C, and also probability of A given H. This is different from that one. These are different. Okay. Here we find these by using Bayes' theorem. We use Bayes' theorem for finding these three. Okay, but these are, it's only the conditional probability. It's easy. And the probability of H, we find it. Let's find them for this example here. So probability of A is probability of making calls by full, which is 40%. It's given in the table. Okay, it says probability of A, we let A denote the event who made the call. So the percentage of who made the call is 40%. That means probability of A is 40. Okay. How about probability B? B is the event that Raqib made the call. It is 25, because 25% of the calls is done by Raqib. And also Li, which we denote by C. We denote by C. You see, it says C is the event that Li made the call. So the probability of it is 35%. Okay, that means here we say since Fu made 40% of the calls, that means probability of A is 0.40, because 40% of the calls is done by Fu. That means the probability of A is 0.40. 40% means 0.40. And also for B and C, you say since Raqib made 25% of the calls, that means probability of B is 0.25. Okay, so this is probability of B. And for probability of C, which is the percentage of the calls which is made by Li, which is made by Li. Okay, these are the answers for the first part of the question. It's the answer for these ones. And then for the second part of the question, it says find the probability of H given A, then probability of H given B, and probability of H given C. Look, the probability of H given A means 20%. It's 20%. Okay. Probability of B given A given probability of H given B is 55%, and also probability of H given C is 30%. Let's see. We say, given that Fu made the call, it's given. Since Fu made the call, so the table shows that 20% of the persons hung up is probability of H given A. A is given. Even A is given, which is the call made by Fu. Okay. So what's the percentage of hung up? For that case is 20%, which is 0.20. That's the probability. Look, this is A. This is A. Okay. It says if we have given A, so what's the hang up for A? It is 20%. So the probability of H given A is 0.20. And then for B, this is B. Okay. We say the probability of H given B is 55%, which is the probability is 0.55. And then for C, it is 30%, which is 0.38 probability. The probability of H given A is 0.20. The probability of H given B is 0.55, and also the probability of H given C is 0.30. These are the probabilities of H given A, H given B, and H given C. So what about the probability of A given H? How about this one? How about the probability of A given, B given H? And also the probability of C given H. Here, we cannot find this by the previous way. We must apply the Bayes theorem for finding these three. Okay? We must apply the Bayes theorem for finding these three. Let's apply it. Here, we have A, B, and C, and also H. Okay? Look, we apply this rule. We apply this rule. Here, A, B, and C denotes B1, B2, B3 here. Okay? And also H denotes A here. Look. We say the probability of A given H is probability of H given A times probability of A dividing by probability of H given A times probability of A plus probability of H given A given B, times probability of B plus probability of H given C times probability of C. We found these all in the previous steps. Okay, in step 1 and 2, we found these all. As you see here, we found probability A, B, and C. And also we found probability of H given A, H given B, and H given C. We just put these values into this rule. So you will get the result. Probability of H given A is 0.20. Probability of A is 0.40. Then in the denominator we have probability of H given A times probability of A plus probability of H given B times probability B plus probability of H given C times probability C. Here we found these all before. So you just replace them by their values. These are the values of them. And we get 0.248. That means the probability of A given H is 0.248. Okay, but the probability of H given A is 0.20. These are different. Okay, so this is Bayes theorem. This is Bayes theorem. Then for probability of B given H, it equals to, we do the same, only the numerator is going to be changed. Only the numerator. Here the numerator is probability of H given A times probability of A. Only that one is going to be changed. It becomes probability of H given B times probability B, and the denominator is the same. Denominator is the same. So it's probability of H given B times probability of B. Denominator is the same. It's the same. Okay, this is the rule. This is the rule. And here we found probability of H given A given B given C. And we also found the probability of A, B, and C. That's given in the table. We just put these values here to get the results. Okay. So the most important thing here is to know this rule. If you know this rule, other steps is only substituting the values. And for probability of C given H, as I said, only the numerator is going to be changed. It becomes probability of H given C times probability C, and the denominator is the same. And you get 0.326. And then in the last step, we are asked to find the probability of H. Probability of H. Probability of H is down. It's only the denominator. It's only the denominator in the Bayes theorem. Probability of H is only the denominator in the Bayes theorem. So this denominator is this one is probability of H. It's probability of H given A times probability of A. Probability of H given B times probability B. Probability of H given C times probability C. We found these all before. We just plug in these values to get the result, which is 0.3225. Is it difficult? It's so easy. If you just know that rule, it's easy. Do you have any question? Here you have another example. The ELI is A. I'm just going to do it by ELISA, okay? The ELISA test is used to detect antibodies in blood and can indicate the percent of the HIV virus. It says approximately 15% of the patients at one clinic have the HIV virus. That means 15% of the people or of the patients at the clinic have HIV virus. Among those that have the HIV virus, approximately 95% test positive on the ELISA test. We have only 95% positive tests among those that have the HIV virus. And among those that do not have the HIV virus, approximately 2% test on the ELISA test. It's positive. We have only 2% positive tests among those which have no HIV virus. It says find the probability that a patient has the HIV virus if the ELISA test is positive. It says if it's positive, then find the probability that the patient has the HIV virus. Here, we let H denote the event. Patient has HIV virus. Okay, and T denote the patient doesn't have HIV virus. You have two cases. The patient is either has HIV virus or doesn't have HIV virus. So the probability of H is 15%. It's given. It's 15%. And also the probability of T is 85. Why? Because you see, those which have HIV virus and those which have no HIV virus. So the probability of both must be 1. The probability of those which have HIV virus is 0.15. Probability of H is 0.15. Here you say P of H plus P of T, which is those which have no HIV virus, is 1. P of H is given in the example, which is 0.15 plus P of T equals 1. How about P of T? The probability of T is, we move this to the right hand side. We get 1 minus 0.15. That means P of T is 0.85. This is the probability of those which have no HIV virus. We let POS denote the feature test positive. POS is the test is positive. Denote the test is positive. So the probability of POS given H, POS given H. Here we have POS with two other cases, H and T. The probability of POS given H is 0.95. It's given above. It says 95 of the tests are positive among those which have HIV virus. It's given that. It says 95 of the tests are positive among those which have HIV virus. Here we do not H to be the patients has HIV virus. That means the probability of POS, which is positive test, given that the patient has HIV virus, is 0.95. It's given. And also the probability of POS given T is 0.02. That's also given. So these are only the needed things that we should have. Now, how about the probability of H? Sorry, let's ask. Find the probability that a patient has the HIV virus if the ELISA test is positive. That means the probability of H given POS. This equals what? Here we must apply the Bayes theory. Okay. We say it is the probability of POS given H times probability of H dividing by probability of POS given H times probability of H plus probability of POS given T times probability of T. This is the Bayes theory. Okay, here we have only two cases. It's either have HIV virus or not. We do not the HIV virus for H, and if the patient has no HIV virus, is T. So this is the rule. And we have these all. We have probability of POS given H, which is 0.95. We also have probability of H, which is 0.15. That's for the numerator. And for the denominator, we have the same. This is the same. We have that. And also probability of POS given T, we have that, which is 0.02. And also we have probability of T. We have given these all. We just replace them by their values. We get the result, which is 0.893. But be careful, it must not exceed 1 and 0. Okay, it must be between 0 and 1. The result of all the probabilities must be from 0 to 1. It's possible to be 0, and it's also possible to be 1, but not greater than 1 and less than 0. So this is the result. We just apply the Bayes theory. It's so easy. Now we have another example. It says Hannah, Amir, and Danny write a program that schedule tasks for manufacturing toys. The table shows the percentage of the code written by each person. That means here 30% of the code is written by Hannah. 45% of the code is written by Amy. And also 25 of the code is written by Danny. And the percentage of buggy code for each person. Buggy code means errors, okay? Here, the percentage of the bugs, 3% of the bugs is done by Hannah. 2% of the errors is done by Amir. And also 5% of the bugs or errors is done by Danny. Okay. So here we have this table. It says, given that a bug was found, find the probability that it was in the program code written by Dan. It says a bug is found, find the probability that if this mistake or wrong code is written by Dan. Here, we let H denotes the event code written by Hannah. A denotes the event of code written by Amir. D denotes the event of code written by Danny. Okay. B denotes a bug found in code. Here we should find the probability of. It's given that B is found. So what's the probability that F is in Danny's program? We found this. As you see in the question, it says it's given that a bug was found. That was given, we must write down the second one. This given. Here we have 3 cases. The code is written by Dan, the code is written by Emily, and the code is written by Hannah. Okay. Here we just apply the bias theory. It's so easy. So the probability of D given B is, I'm just going to write down here. Okay, that's written here. Okay, we say the probability of D given B equals the probability of B given D given A. Let's see H. I'm gonna write down it's in order. Times probability of H dividing by probability. This is D, not H. Sorry, it's D. It's D. And for the denominator, I'm gonna write down H. Here, probability of B given H times probability of H plus probability of A given H. What's that? Sorry. B given H, probability H. Then probability of A, B given A times probability of A plus probability of, I'm right down below here, plus probability of, we have 3D, okay. Probability of B given D times probability of D. Let's find the probability of these probabilities. Here from the table, the probability of H, this is H, this is A, and this is D. That means the probability of H is 30%. Probability of A is 45%. And also probability of D is 25%. It's given in the table. It is H, this is A, and this is D. And also the probability of B, this is B. These all are B. Okay. B given A is 3%, it's 0.03. And probability of B given A is 0.02. And the probability of B given D is 0.05. From the table, we can find these all here. Since Hannah wrote 30% of the code, that means probability of H is 30%, which is 0.3. And similarly for A and D, since the code is written, since 45% of the code is written by Amir, so the probability of A is 0.45. And the and 25% of the code is written by Danny. That means probability of D is 0.25. These are the probabilities of H, A, and D. Now, to find the probabilities of B given D, B given H, and B given A. We say if Hannah wrote the code, the table shows that 3% of the bugs was found. 3% of the bugs was found. That means probability of B given H is 0.03, since it's 3 of 100, 3%. That is 0.03. Okay, that's given above. And also probability of B given A, if the code is written by Amir, then we could find 2% of the bugs. That means probability of B given A is 0.02, and also probability of B given D is 0.05. These are the probabilities. Now we plug in these into this row here, into this row. We get the result. But here in the handouts, later, check it out. Certain probability B does to probability B chia. Jere kerteke. Jere kerteke katachi. Probability B given H times probability H plus probability B given A times probability of A plus probability of B given D times probability D. These are those. This is the denominator. In the numerator, we have probability of B given D times probability D. So you have probability B given D times probability D dividing by probability of B. Probability B is the denominator. Okay. So it is 0.1498. As you see, this is between 0 and 1. Okay. So the probability of D given B is this. How about probability of A given B? A given B equals what? Here only the numerator is going to be changed. We just replace D by A in the numerator. Here, this becomes A and this becomes A. How about H? Probability of H given B. And here, we just replace this by H or by A. Okay. When do we use these? If in the example or if in the question, it asks for the probability it was found in the program. So the probability was written by Hannah, we find for H. And if it's done by Amir, we write down for A. That's all. Only the numerator is going to change. And here in this example, we just apply the Bayes theorem. Do you have any question? Okay, let's take a break for 10 minutes. We now have independent events. We say if the probability of event A doesn't depend on event B. Here we have two events such that none of them depend on the other one, in the sense that probability of A given B equals probability of A. That means probability of A doesn't depend on probability of B. And also event A doesn't depend on event B. We see that A and B are independent events. Here, in this case, if probability of A given B equals probability A, we say A and B are independent. Probability of A given B equals probability of A intersection B over probability B, which equals probability of A. It is probability of A. Why? Because probability of A intersection B equals probability of A times probability of B. Why? Because these two events are independent. There is no intersection point between them. There's no intersection between probability of A and probability B. Between A and B. There is no intersection between these two events. So the probability of A intersection B is probability of A times probability B. Here, probability B with probability B are cancelled out. So what's left? Only probability of A. That means probability of A given B equals probability A. Here, let's written that probability of A intersection B is probability A times probability B. You see, to find the probability of two independent events that occur in sequence, find the probability of each event occurring separately. We find probability of event A and event B separately. Then we multiply them. We get the probability of A intersection B. And this multiplication rule is defined symbolically. Here, probability A and B equals probability A times probability B. Probability A and B equals probability A dot probability B. We find probability A and probability B separately, then we apply the results to get the probability of A and B, or probability of A intersection B. Here we have some examples about independent events. The first one is landing on heads after tossing a coin. After tossing a coin, landing head, and rolling a 5 on a single side die. لهالداني parts die كان زي أجريك بنشر من دسكت. هروها هالداني شيء لا هالداني بردزارجة بينج من دسكت. أندوان دوشتي جوازه. Okay. هيك يعني اعتماد ناكر السرير. وأندوانا independent event. For the second one, the second example is choosing a marble from a jar and landing on it after tossing a coin. And these two are independent to each other. And the example, choosing a 3 from a deck of cards, then replacing it, and also then choosing an ace as the second card. على أجر كم ديك يعني بستيك ورقة معها بياري ورقة سيدر بيني بيكين الناي دواتر بالليدر بيني ايش معناه بالليدر بيني أم دوانا دوشتي جواز حقاني بسريكو هيتش يعني كاريجري ناكا سريكو. So these two events are independent. And for the last example here, it's rolling 4 on a single 6-sided die. When we roll a dice, and we get 4, and then we roll it again. we roll it again. And getting 1 in the rolling exercise dice. Okay? Lera berdezari halayın. Şu armandas evet. Okay? Safari ke berdezari ke halayın. Yek mandas. Am duani hiç ihtimalı kan istedi. Hiç karigeri nasıl yani? Aman yek bir du bir sev. Karigeri ne nasıl bitiriyan çanne. Okay? So these two are two independent events. We now have another example. An example. A coin is loaded so that the probability hits is 0.6. That means the probability of getting a hit is 0.6. We have a coin, we toss it. The probability of getting a hit is 0.6. So what's the probability of getting tail? Yeah, it's 0.4. That's 0.4 because the sum of these two must be 1. 0.6, then 0.4, the sum of them is 1. Suppose that the coin is tossed twice. We toss the coin twice. Although the probability of heads is greater than the probability of tails. Of course, because the probability of heads is 0.6 and probability of tails is 0.4. There is no reason to believe that whether the coin lands heads or tails on one toss will affect whether it lands heads or tails on the second toss. لحظاني يكم جارا شير بيان خد كاريگري نيه لسر كاتا امدو ايفنتا كاتا كدو جار درايك عليين اما تشيه اما independent event. Okay, thus it's reasonable to assume that the results of toss are independent. So here in rolling or tossing a coin twice, these two events, you have two events. Event 1 is tossing the coin for the first time. That's event 1. Event 2 is tossing the coin for the second time. These two events are independent to each other. None of them depend on the other one. It says, what's the probability of obtaining 2 heads? What's the probability of obtaining 2 heads? First, the most important here is to write down the sample space. What's the sample space in tossing a coin twice? Look, the sample space is either both head or the first one is head and the second is tail. The first one is tail and the second is head, and both are tail. Okay, we have only these 4 elements in the sample space in tossing a coin twice. We let A denote obtain head on the first toss. On the first toss, obtaining head, we denote by A, and we denote B to be obtaining head on the second toss. As it's given in the example, it says we toss the coin twice. We say we let A to be getting head in the first toss and B getting head in the second toss. Okay. Here, probability A equals probability B, and it's also equal to 0.6 because it says it's given that in the example, getting head, the probability of getting head is 0.6. So it's the probability of A complement, which is the probability of tail. It equals to 0.4. How about the probability of B complement? It's the same because the probability of B is 0.6. So its complement is 0.4. It must be 0.4. Okay. This is probability of tail. This is also probability of, let's say tail 1. Probability of tail 2. In the second, I mean in the first choice and second choice. Now we are going to find these all. It says, what's the probability of obtaining 2 heads? Probability of obtaining 2 heads. Here we have 2 heads in one of the elements of the sample space. 2 heads. The first one's head is 0.6 and the second head is 0.6. We multiply these two, we get the result because these two are independent. We say probability of head and head equals to what? We apply the above rule here. It says if A and B are 2 independent events, then probability of A and B equals probability of A times probability of B. Here we have probability H and H, which is head and head. Probability of head is equals to probability head times probability of head. Is it? Probability of head is 0.6 and this is also 0.6. Multiplying these two is 0.36. So this is the probability of both tossing coin is head, to be heads. This for the first question here. This answer for the first question is 0.36. And it's also solved here. What's the probability of obtaining 2 heads? It is this intersection. This is multiplying. That's all. Okay. This is intersection. This is multiplying. We say probability of 2 heads is probability of A intersection B. Why A intersection B? Because we let A to be first head, to be the first head, and B to be the second head. Okay, we say this probability of A times probability of B. Probability of first head is 0.6. It's given that getting head is 0.6, and then probability of head in the second time is also 0.6, which is 0.36. This is the probability of 2 heads. For the second part, it says what's the probability of obtaining 1 head? Obtaining 1 head. Let's return to the sample space. To get 1 head, we have these 2 cases. In these 2 cases, we have 1 head. Okay. For this one, for the first time, to get 1 head, if the first one is head, we say it's probability of A times probability of B complement, because the second time is tail, it's not head. Okay, here I said B complement is in the case if the second one is tail, and probability of A complement is tail for the first one. So here for this one is probability of A times probability of B complement, and for this one is probability of A complement, because the first one is tail, it's not head, times probability of B. We just find these and the sum of them. That's the result. So let's find it. You see this multiplication, sorry. Okay. This is intersection, and this plus. This is multiplying. This is multiplying. That's one. Here we say probability of one head. It's either the first one is head and the second is tail, or the second is head and the first is tail. Okay. We say probability of A intersection B complement. That means if the first one is head, we do not A to be head for the first time, and we do not B to be head for the second time. We say if the first one is head and the second is tail, let's be complements, because the complement of head is tail. And if the first one is tail and the second is head, as you see here, it's written B complement, A complement, intersection B. This is A complement, intersection B. Here you find these probability of A intersection B complement. These two are two independent events. As probability of A times probability of B complement. And also probability of A complement intersection B is probability of A complement times probability B, because these are two independent events. Here probability of A is given, which is 0.6. Probability of B complement is 1 minus 0.6, which is 0.4. We found before. So 0.4. And probability of A complement is 0.4. Probability of B is 0.6. We just multiply these, so we get 0.24 plus 0.24 is 0.48. That means it's 48%. The probability of one head is 0.48. It's for the second part of the question. For the third part, it says, what's the probability of obtaining no head? That means both are tails. Both are tails. Here, in this case, we say it's probability of A complement intersection B complement. Is it? Because A complement denotes tail and B complement denotes tail also. It equals to probability of A complement times probability of B complement. This is 0.4. This 0.4 multiplying them is 0.16. That's it. Here, it is probability of A complement intersection B complement. Probability of no heads. No heads means both are tail. The first one is A complement and the second is B complement, because A and B denote the heads in both in both events. Here it is probability of A complement times probability B complement. Probability of A complement is 1 minus 0.6, because probability of A is 0.6. So probability of A complement is 1 minus 0.6, which is 0.4. And probability B complement is 0.4. Multiplying them is 0.16. That means the probability of no head is 0.16. This answer for the third part. And for the last part, it says, what's the probability of obtaining at least one head? At least one head. If you look at the sample space here, at least one head, we have this, and that. We just have not this one. Okay, and the probability of this one is 0.16. That's it. We just say 1 minus 0.16. Okay, because we have only two parts. All the sample space is two parts. It's either both tail or we have at least one head. Okay, or it means no heads or at least one head. Here, the probability of no heads is 0.16. So what's the probability of at least one head? It is 1 minus 0.16, which is 0.84. Okay, and also you can find by here for this one. It says probability of A times probability B plus, for this one, probability of A times probability of B complement. Is it? Because here the second is tail. And for this one, it's probability of A complement times probability B. We find these and then the sum of them. You will get the same. Let's see. Here we have the probability of 1 head. Probability of 1 head, it's either 1 head or 2 heads. We found these before in the first and second steps. In the first step, we found the probability of 2 heads. And in the second step, we found the probability of 1 head, which is 0.48. The sum of these two is 0.84. Okay, that is 0.84. Or you can use this one this way. 1 minus probability of no head. We found this is 0.16. 1 minus 0.16 is 0.84. You get the same result. You can use either the above or this one. Okay, that's so easy. Okay, do you have any question? Here we have on the example. It says a dresser drawer contains 1 pair of socks with each of the following colors. We have a pair socks of blue color, brown, red, white, and black. Here we have 5 pair of socks. 5 pair of socks, and each one is different color. It says each pair folded together in a matching set. You reach into the socks drawer, and choose a pair of socks without looking. Just take a pair of socks without looking at the socks. You replace this pair, and then you take another one. You take a pair of socks again, not another one. You take a pair again. It says, what's the probability that you choose red pair of socks both times? Here we have 5 pair of socks. We have 5 pair of socks. You're gonna take one random, then you return, and you take another one random. Okay, for the first time you took it from 5 pair of socks. You have 5 pair of socks. You take one. It says, what's the probability that if this one is red, how many red do we have in it? We have only 1 red. We have 5 pair of shoes of socks, and each one has a different color. What's the probability that if you pick a red one? It's 1/5. That means the probability of red is 1/5. It's for the first time. We return it. Since we returned it, it's the same for the second time. It's the same for the second time. That means probability of red and red. The first one and second time, the first and second time to be red is probability of red and red. What's probability of red times probability of red? It equals to 1/5 times 1/5, which is 1/25. This is the probability that if in both times we get the red socks. Okay, how about the blue one? It's the same. How about if the first one is red and the second is blue? It's the same. It's 105 times 105. We have another example. A card is chosen at random from a deck of 52 cards. It's then replaced and a second card is chosen. First, we choose a card. Then your turn. Again, we choose a card. It says, what's the probability of choosing a jack and an 8? A jack and an 8. And the first time is a jack and the second time is an 8. Look, the probability of jack is 4 over 52. Since the total number of cards is 52, and this deck of cards, we have 4 from each of the cards. 4 ace, 4 ones, 4 let's say K's, J's, all. Okay, here we say, what's the probability that if we take a jack and an 8? So probability of jack is 4 over 52 because we have 4 jacks in the deck of the cards. And probability of 8 is also the same. It's 4 over 52 because we returned it. If we didn't return it, if you don't return it, it is 4 over 51. Okay, it becomes 51 because we took a jack from it. Then probability of jack and 8 is probability of jack times probability of 8. Probability of jack is 4.52 and probability of 8 is 4.52, which is 16 over 2,704, and we can reduce. It becomes 1 over 169. This is the probability of taking a jack and an 8. For all the other numbers, the same. Because for each, we have 4 from the deck of the cards. Here we have a jar contains 3 red, 5 green, 2 blue, and 6 yellow marbles. We have a jar. In the jar, we have 3 red, 5 green, 2 blue, 6 yellow. And the total is 3, 5, 6, and 2 is 16. Is it? The total number of marbles in the jar is 16 marbles. It says a marble is chosen at random from the jar. We just choose a marble from the jar. After replacing it, we return it. Then a second marble is chosen. We take another marble. What's the probability that choosing a green and yellow marble? What's the probability of choosing a green and yellow marble? So what's the probability of green? How many greens do we have? It is 5 over 16. This is the probability of taking a green one. We return it. And then we take a yellow one. The probability of yellow is, how many yellow do you have? 6. 6 divided by 16. So probability of green is 5 over 16 and probability of yellow is 6 over 16. We just multiply these two, we get the probability of green and yellow. Probability of green and yellow is the probability of green times probability of yellow. This is multiplication. This is multiplication, which is 30 over 256. Okay. We just multiply the probabilities because these are independent. Now, the last example in this chapter. Do you have any question about those examples that we talked about? Okay. In this example, it says Halim and Aina take a final examination in Fortran. Fortran is a computer programming language. It's like C++, Java, those, okay? The probability that Halim pass is 0.85. It's for passing. So the probability of pass smaller. Let me write down in a table. Probability of pass of Halim is 0.85. How about probability of fail of Halim? Is 0.15, which is 1 minus 0.85. And the probability that Aina pass is 0.70. So probability of A pass is 0.70. How about probability of A is fail? Is 0.30. Assume that the events Halim passes the final exam, and Aina pass the final exam are independent. It says these two are independent. So passing or failing Halim doesn't depend on passing or failing Aina. So these two are independent events. It says find the probability that Halim doesn't pass. It is 1 minus passing percentage, which is 0.85. 1 minus 0.85 is 0.15. Look here, we let H denotes the event Halim passed the exam, and A denote the event Aina passed the exam. You have two events, okay? Halim passed the exam and Aina passed the exam. So the probability of H complement is, in the first question, it asks about finding the probability of H complement. It is, look, we say H, probability of H is 0.85 because it's about the percentage of passing for Halim. How about probability of H complement? It's 0.15. Probability of A is the percentage of passing Aina, it's 0.70. That's given. So probability of A complement is 0.50. A complement means fail. Okay. If A is pass, so its complement is fail. For the first one, it says find the probability that Halim doesn't pass. Since the probability of passing Halim is 0.85, that means failing here probability of failing here is 0.15. That's 1 minus 0.85, which is 0.15. For the first part. For the second part, it says find the probability that both pass. Both pass. It is probability of H multiplying by probability of A, because H and A do not pass for both. Okay? Multiplying 0.85 and 0.70. That's it. It's probability of A, and H and A is probability of H multiplying by probability of A. Then probability of both fail. Find the probability that both fail. If both are fail, so the probability of failing Halim is 0.15, and probability of failing Aina is 0.30. It's 0.30. We multiply these two, we get the result. It is probability of H complement times probability of A complement. Probability of H complement is 1 minus A, probability of A, which is 0.15. And probability of A complement is 0.30. We multiply these two, we get the result. Then the last part is, it says find the probability that at least one pass. At least one pass. That means it's the probability of none of the, and both are not failed. Okay, we have, let's see, let's write down the sample space. If helium is pass and Ina is pass. Helium is pass, Ina fail. Okay, and also helium fail, Ina pass. Again, helium fail, Ina fail. So what's the probability that at least one of them is pass? It's the complement of probability that both are fail. 1 minus probability of A complement intersection H complement. 1 minus 0.045. And you also can find by finding probability of H intersection A plus probability of H intersection A complement plus probability of H complement intersection A. Find these, it's the same result. You must get the same result. Probability of H intersection A is 0.85 multiplied by 0.70. Probability of H intersection A complement is 0.85 multiplying by 0.30, because probability of A is 0.70. So probability of A complement is 0.30. Probability of H complement intersection A, it is 0.15 times 0.70. And you get the same result as it's written down here. Okay, and it's the end of this chapter. Do you have any question about this chapter? And this is what I talked about today. And even for the chapter, if you have any question about this chapter, you can ask next Tuesday after the class. Okay, you can study up to that time, and if you have any question, you can ask before the test. Okay.